War has a way of turning ordinary engineers into desperate inventors. It strips away academic curiosity and replaces it with a brutal, pressing urgency. In the winter of 1942, this urgency was felt most acutely by the men of RAF Bomber Command. Deep inside a fog-choked airfield in the English countryside, where the damp cold seeped into the bones of both men and machines, a grim calculus was being performed. The numbers were not adding up. The German night fighter force, a lethal combination of sophisticated radar and determined pilots, was tearing British bombers out of the sky with terrifying, surgical precision. The statistics were more than just numbers on a chalkboard, they were a creeping tide of despair. A tour of duty was 30 missions. The chance of surviving it had plummeted to less than 1 in 4. The Luftwaffe's Himmelbett 4-poster bed system was a deadly, efficient machine. German ground-controlled interception radar would guide a Junkers Ju-88 or a Messerschmitt Bf 110 into a box of airspace, where the fighter's own airborne Liechtenstein radar would then lock on for the kill. For the young men in the Lancasters and Halifaxes, it was like being stalked by an invisible predator that could see in the dark. The first sign of danger was often the thud of cannon shells ripping through the fuselage. Every countermeasure the British tried seemed to falter. Early radar jammers, bulky and power-hungry, were inconsistent and easily countered by the Germans' shifting frequencies. Window, the aluminum chaff that had proven so devastatingly effective at blinding ground radar, was useless against the fighter's own short-range, airborne sets. The enemy was adapting, evolving, and the RAF was losing the technological arms race at a cost measured in thousands of young lives. Pilots, navigators, and gunners were dying faster than new crews could be trained. The very foundation of the strategic bombing campaign was crumbling. In the face of this existential threat, the Air Ministry was forced to consider even the most outlandish of ideas. Desperation became the mother of invention. It was in this climate of near despair that they quietly approved a strange, almost philosophical proposal from a small, little-known group of scientists and engineers operating out of a drafty, converted manor house in Dorset. These were the boffins of the telecommunications research establishment, men who thought in wavelengths and circuits. Their proposal was deceptively simple. They wanted to experiment with light. Not the blinding, sweeping cones of searchlights that probed the sky from below. Not the brilliant, descending candles of flares that illuminated the ground. They proposed a new kind of light altogether, a controlled, intense, and precisely timed emission that could be wielded as a weapon. The theory was that a sudden, overwhelming burst of light from the bomber could temporarily blind or at least disorient the pilot of a pursuing night fighter, spoiling his aim and giving the bomber precious seconds to escape. It was a radical, high-risk concept. The Air Ministry knew it could be a war-winning advantage, a shield of pure photons. But there was a terrifying flip side. What if, instead of blinding the enemy, it blinded their own pilots? What if it lit up the bomber like a beacon on a dark stage, making it an even easier target? It was a gamble, a roll of the dice with lives as the stakes. The green light was given, not with fanfare, but with a quiet, anxious hope that these men in their Dorset laboratory might just bend the laws of physics to their will. The device that emerged from the Dorset laboratory did not look like the future. It looked, to the cynical eyes of the RAF flight lieutenant sent to assess its progress, like a half-broken shoebox filled with the guts of a radio and a witch's familiar. It was a crude, hand-soldered mess of capacitors, resistors, and hastily switched wires, all housed in a wooden crate that still showed traces of the oranges it once carried. At its heart was a glowing glass tube that hummed with a distinct, high-pitched whine, like an angry wasp trapped in a jar. The scientists, with their characteristic dry humor, had christened it the emission stabilizer, a name so bland and bureaucratic that it bordered on deception. In truth, nobody, not even its creators, was entirely sure what it actually stabilized. The nomenclature was a shield, designed to deflect attention and manage expectations. The original idea was brutally straightforward. Create a controlled flash of intense, pulsed light from a housing on the bomber's tail that could momentarily confuse a pursuing night fighter. The concept was a literal burst of daylight, right in the enemy pilot's face. They envisioned a strobe-like effect that would overload his night-adapted vision, painting his cockpit with a sudden, blinding whiteness and ruining his aim at the critical moment. But the path from theory to reality was a gauntlet of spectacular failures. The initial tests, conducted in a blacked-out hangar, were disastrous. The wiring, unable to handle the sudden, massive power surge, would overheat and melt, filling the air with the stink of burning insulation and ozone. The fragile glass tube, the key to generating the light pulse, kept shattering under the thermal stress, scattering shards of glass and phosphor across the workbenches. The capacitors, bulky and volatile, sometimes exploded with a sound like a pistol shot. One particularly ambitious prototype, drawing far more power than intended, arced across its housing and set a canvas hangar wall smoldering, nearly burning the entire facility to the ground. Morale in the small team plummeted. The project was a laughingstock among the other, more established groups at Trey. Reports filtered back to the Air Ministry suggesting the Dorset folly was a waste of precious resources. The project was weeks, perhaps days, from being officially cancelled and its team scattered to more productive endeavors. The breakthrough came not from a moment of brilliant inspiration, but from a tired observation. It was late. The hangar was cold, lit by a single, dangling bulb. The team had just run another test, and another failure. The emission stabilizer had sputtered, its light pulse weak and unfocused, flickering like a dying candle. The lead physicist had already left, dejected. Only a young, junior engineer remained, tasked with packing the equipment away. His name was Alistair Finch, and he was exhaustedly tracing a circuit with a multimeter for the third time. As he reached to disconnect the main power lead, his hand brushed against the device's housing. The tube gave one last, feeble pulse. In that instant, Finch wasn't looking at the target downrange. He happened to be looking down at the clipboard in his lap, at the schematics he was holding. The weak, dying light from the tube didn't blind him. Instead, it illuminated the papers perfectly. Every line, every notation was thrown into sharp, clear relief. He could read it as if under a desk lamp, despite the hangar's gloom. He sat there for a long moment, the hum of the dying device the only sound. The target, a photometer designed to measure flash intensity, had registered nearly nothing. A failure. But Finch had seen something else. He wasn't trying to create a destructive flash anymore. He had accidentally created a perfect, localized, and cold source of illumination. The pulse didn't blind the pilot. It illuminated his instruments. From inside the cockpit, the dangerous idea had just taken a completely unexpected, and far more valuable, turn. Finch's observation was met with initial skepticism. The project's lead, Dr. Evelyn Thorne, a physicist who had fled Berlin in 38, listened to his breathless report with a weary expression. She had spent months chasing the dream of a photonic weapon, and the idea that their abject failure might be a success in disguise seemed like the desperate hope of a junior staffer. But Finch was insistent. He set up a simple demonstration. That night, in the pitch-black hangar, he placed the recalcitrant emission stabilizer on a workbench. Opposite it, he set up a standard RAF pilot's instrument panel, salvaged from a crashed Wellington. He invited Dr. Thorne to stand at the pilot's position. The hangar was so dark she could barely see her hand in front of her face. The familiar, comforting glow of the instruments was completely absent. "Now," Finch said, his voice tight with anticipation. He threw the switch. There was no blinding flash. Instead, a soft, cool, and incredibly focused pulse of light emanated from the device. It wasn't a diffuse glow that lit up the entire hangar. It was directed, almost like a painter using a brush, and it washed over the instrument panel with a ghostly luminescence. Every dial, every gauge, every needle was perfectly illuminated. Dr. Thorne could read her airspeed, her altitude, her Euro compass with crystal clarity. The light was intense yet somehow gentle on the eyes, and it vanished as quickly as it appeared, leaving no afterimage, no ruined night vision. The silence in the hangar was profound. The failed weapon had just become a revolutionary tool. They had stumbled upon the principle of localized, non-destructive illumination. The problem their device was now solving was one they hadn't even known was a primary concern, the fatal compromise of night vision. Inside a bomber's cockpit, a pilot had two terrible choices. He could fly in near total darkness, relying on his instruments being faintly lit by dim, red-filtered bulbs that were meant to preserve his night vision. But this made reading charts, checking complex settings, or dealing with emergencies difficult and slow. Or, he could turn on a white light, a map light, a torch, which would instantly destroy his hard one-night adaptation, blinding him to the world outside the cockpit, to the shapes of other aircraft, to the glint of an enemy fighter. It was a choice between being blind inside or blind outside. This device offered a third way. A way to see the instruments with perfect clarity, for a fraction of a second, without any perceptible impact on one's ability to see into the darkness. It was, as Finch scrawled in his lab notes that night, like lightning that only strikes the page you are reading. The goal of the project was instantly, radically, redefined. They were no longer building a weapon to blind the enemy. They were building a system to enlighten their own pilots. The emission stabilizer was dead. A new name was chosen, one that reflected its new, elegant purpose, the transient illuminator. The race was no longer to create a bigger flash, but to perfect a faster, more reliable, and more precise one. They had stopped trying to fight the dark. They had learned, instead, to borrow from it. Transforming the transient illuminator from a promising lab curiosity into a rugged, reliable piece of avionics was a new war in itself. The shoebox prototype was a long way from being able to survive the vibrations of a Lancaster's 4 Merlin engines, the brutal G-forces of evasive maneuvers, or the extreme temperature swings from the tarmac to 20,000 feet. The team, now reinvigorated and operating with a new sense of clarity, attacked the problems with ferocious focus. The fragile glass tube was encased in a shock-absorbent rubber and steel housing. The temperamental wiring was ripped out and replaced with heavy-duty, shielded cable used in naval gun directors. The power supply, once a haphazard collection of overstressed capacitors, was completely re-engineered around a robust, rotary transformer that could deliver a massive, precise jolt of electricity on demand. The key innovation was the trigger mechanism. How would a pilot, his hands full with the controls, his mind racing in combat, activate the light at the exact moment he needed to read a gauge? The solution was elegant in its simplicity. Instead of a switch, they created a demand system. A small, palm-sized button was mounted on the control yoke. The pilot simply had to squeeze it. The system was designed with a brief recharge cycle, preventing it from being held on continuously and defeating its own purpose. It was a tap, not a toggle. A sip of light, not a flood. The first operational tests were conducted not over Germany, but in the skies over the Scottish Highlands. A specially modified Lancaster, its cockpit interior fitted with light sensors, took off on a pitch-black night. The results, radioed back to a breathless team on the ground, were even better than they had hoped. Pilots reported a revelation. They could check their engine settings, confirm their navigator's course corrections, and even read a complex fuel transfer checklist without ever needing to fumble for a torch or strain their eyes in the dim red glow. Their night vision remained pristine. One veteran pilot, a squadron leader with over 40 missions, landed and told the scientists, "It's like having a faithful clerk sitting beside you, who only speaks when spoken to, and only to tell you exactly what you need to know." The implications were enormous. This was no longer just about convenience, it was about survival. A pilot who could keep his night vision could spot the faint silhouette of a German night fighter a crucial second earlier. A navigator who could read his charts instantly and accurately could keep the aircraft on a safer, more efficient route. The reduction in cockpit errors was immediate and measurable. The transient illuminator didn't shoot down enemy planes, but it prevented the mistakes and delays that got friendly ones shot down. By mid-1944, the devices, now officially designated the TIMKI, were being fitted to all new Lancaster and Mosquito night bombers. The order came from the highest levels of bomber command. The accidental discovery in a blacked-out hangar was now a standard, if still secret, piece of kit. The boffins in Dorset had set out to create a sword, but had instead forged a shield. And in the brutal arithmetic of aerial warfare, a good shield was often worth a dozen swords. The end of the war in 1945 saw the TIMKI quietly phased out of service. Its specific military purpose had ended. The reports were filed away, stamped, secret, and the story of the desperate attempt to build a light weapon that became an illumination tool was largely forgotten, subsumed by the grander narratives of D-Day, the atomic bomb, and the jet engine. But the principle it embodied, the concept of transient, on-demand, localized lighting, did not die. It had been proven, refined, and understood. The scientists who worked on the project returned to civilian life, taking their knowledge with them. In the 1950s, the first commercial strobe lights began to appear, based on the same capacitor discharge technology perfected for the transient illuminator. They were used in photography, of course, but also in lighthouses and airport beacons, where a powerful, brief flash was far more effective and energy efficient than a continuous beam. The true, ubiquitous legacy of the Dorset experiment, however, emerged decades later. As microprocessors shrank and electronics became cheap and reliable, the concept of a brief, user-demanded pulse of light found its perfect application. The faint, red glow of an alarm clock in a dark bedroom. The gentle backlighting of a car's key fob, illuminating the door lock. The soft, momentary glow from a laptop's power button. The flashlight on a mobile phone, activated with a tap and turning off just as easily. Every time we press a button to briefly light up a small, specific area without flooding the entire room with light, we are using the direct philosophical and technological descendant of the transient illuminator. We are employing a solution born from the desperate need of a World War II bomber pilot to see his instruments without losing his ability to see the enemy lurking in the dark. The engineers in that drafty Dorset laboratory weren't just trying to win a battle, they were, without knowing it, shaping the subtle interaction between humans and technology in the dark. They helped create a world where we can command light to appear exactly where and when we need it, and then vanish without a trace. The WW2 experiment that aimed to create a weapon of war accidentally gave us a small, quiet, and profoundly useful tool of peace, A fleeting kiss of light in the darkness, a final, peaceful victory pulled from the jaws of a wartime failure. The air in the Dorset hangar was thick with the smell of ozone, solder, and damp wool. A week had passed since Alistair Finch's revelation, and the team had worked around the clock, their initial despair replaced by a feverish, focused energy. The goal was no longer a flash, but a controlled, reproducible pulse of illumination. Dr. Thorne had reoriented the entire project. The emission stabilizer was now the transient illuminator, and their new prototype, Mark II, was a slightly less haphazard collection of components, now bolted to a metal plate for stability. The objective of this night's test was to measure the consistency of the light output. Finch, his eyes ringed with fatigue, had set up a bank of photoelectric cells around a mock-up of a pilot's instrument panel. The device was aimed not at the panel itself, but just above it, designed to bathe the area in a soft, general light. Dr. Thorne watched, arms crossed, her expression one of cautious scrutiny. "Powering up," Finch announced, his voice tight. The familiar, angry wasp hum of the glass tube filled the space. He counted down. 3, 2, 1. Pulse initiating. He threw the switch. There was a faint crackle, and then something impossible happened. The inside of the cockpit mock-up didn't just get brighter. It glowed. Not from a single point source, but evenly, uniformly, as if the very air had been infused with a soft, ethereal radiance. There were no shadows. No harsh glare from the glass of the instruments. No bright hotspots or deep pools of darkness. It was a light so perfectly distributed it seemed unnatural, a painter having washed the entire scene with a single, luminous brush. Finch stared, his hand frozen on the switch. This wasn't right. The light from their tube was supposed to be directional, a beam. This was everywhere. Dr. Thorne stepped forward, her scientific detachment evaporating. "Where is it coming from?" she whispered, not to Finch, but to the air itself. That was the mystery. It didn't seem to be coming from the bulb at all. The tube itself was pulsing, yes, but the light filling the cockpit was different, softer, cooler, more diffuse. Finch, moving as if in a trance, reached out and shut off the main overhead hangar light, plunging them into near-total darkness save for the eerie glow from the cockpit. Now, the phenomenon was undeniable. The metal panels of the cockpit mock-up themselves were glowing. A faint, persistent, greenish-silver luminescence clung to the aluminum surfaces. It was as if the metal had been imbued with a gentle, internal fire, emitting the light rather than merely reflecting it. The light from the tube had acted as a trigger, but the panels themselves had become the source. The glow lingered for a few seconds after the pulse ended, fading slowly like the dying embers of a ghostly fire. The team, Finch, Dr. Thorne, and 2 other assistants who had gathered, stood in a stunned semicircle, their faces bathed in the unearthly light. No one spoke. The only sound was the faint dripping of water from a leak in the hangar roof. They had been trying to build a better flashlight. They had instead summoned a phantom. When the glow finally faded, leaving them in profound darkness, Dr. Thorne finally broke the silence. Her voice was low, charged with a mixture of awe and scientific fervor. What, in God's name, was that? They had not created a directed light source. They had not perfected their transient illuminator. They had accidentally discovered something far more profound. The intense electrical field from their pulsed power supply, interacting with the specific alloy in the factory-applied paint on the mock-up cockpit panels, had caused the material to fluoresce. But this was more than simple fluorescence. It was a sustained, cool light emitted directly from a solid material under the influence of an electric field. They had stumbled, blind and lucky, into the realm of electroluminescence. A phenomenon where a material emits light in response to an electric current passing through it, or to a strong electric field. It was a concept that had been observed in certain crystals in laboratories, but never like this. Never so uniform, so controllable, and certainly never on a practical, large scale like a sheet of aircraft aluminum. This was something no one had planned. It was not in the project brief from the Air Ministry. It was not a theorized outcome of their work on defensive flares. It was a complete accident, a side effect, a ghost in the machine that had just pointed them toward an entirely new technological frontier. They had been digging for coal and struck a diamond seam. The report Dr. Thorne sent to the Air Ministry was uncharacteristically breathless. It bypassed the usual dry technical jargon and spoke of a paradigm shift in airborne illumination. Attached were developed photographs of the glowing cockpit mock-up, the images grainy and surreal, looking more like a spiritualist's seance than a military report. This time, the response was not skeptical silence. It was immediate, urgent, and carried the highest priority. The Air Ministry suddenly cared very, very much. A delegation of senior officers and civilian advisors descended upon the Dorset facility. They saw a demonstration, and like the scientists before them, they stood in rapt silence as the unearthly glow manifested on the metal panels. They instantly grasped the monumental implications. The problem of cockpit lighting had been a persistent, deadly thorn in the side of the RAF. Pilots flying long, harrowing bomber missions over blacked-out Europe needed to see their instruments. But traditional solutions were a cascade of compromises. Dim, red-filtered bulbs helped preserve night vision but made precise reading difficult. A single white map light could destroy a pilot's night adaptation for 30 minutes, leaving him blind to the outside world, a death sentence if a German fighter was lurking. Bulbs burned out, their filaments fragile and susceptible to vibration from engines and flak. Reflections on the inside of the curved perspex canopy could create phantom images, confusing a pilot already operating at the edge of his endurance. But a glowing surface. The officers saw its perfection immediately. It was shadowless. The light came from the entire surface of the panel behind the instruments, meaning the gauges were illuminated evenly, with no deep shadows to obscure critical numbers. It was even. No hot spots, no dim corners. Every instrument, from the airspeed indicator to the altimeter, received the same perfect amount of light. It was cool to the touch. No hot bulbs to cause burns or pose a fire risk in an oxygen-rich environment. It was almost immune to vibration. With no fragile filament, the system could withstand the brutal shaking of a damaged aircraft or evasive maneuvers. And it required minimal electricity, a trickle of power compared to the hungry amp draw of incandescent bulbs. The directive from the ministry was simple and stark: make it work. Now. The following weeks were a blur of frantic, focused activity. The Dorset team was expanded, given priority access to materials and technical expertise. The challenge was no longer discovering the effect, but harnessing it. They experimented with different substrates, moving from the accidental aircraft aluminum to thin, flexible sheets of plastic. They worked with chemists to develop phosphor coatings that would glow brighter and longer when subjected to an alternating current. They learned they didn't need the violent pulse of the transient illuminator. A simple, low-power, high-frequency AC current was enough to make the panels glow with a steady, serene light. Within a month, they had their proof of concept. A Vickers Wellington bomber, a sturdy, geodetic workhorse of the RAF, was towed into their hangar. Working day and night, a team of fitters and engineers carefully lined the entire cockpit with the new material. Thin, paper-like sheets, coated with the secret phosphor blend, were adhered to the instrument panel, the side consoles, even parts of the roof. Wires, thin as thread, were run to a small, humming power inverter. The test flight was scheduled for a moonless night. The senior ministry officials returned, their faces grim with the weight of expectation. The Wellington's crew, briefed only on the basics, sat at their stations, their curiosity palpable. From the outside, nothing seemed amiss. The pilot went through the startup procedure. The twin Bristol Hercules engines coughed to life, their deep rumble shaking the airframe. Then, the moment of truth. The pilot, following instructions, flipped a small, unmarked switch on his newly modified panel. The cockpit didn't fill with light. It simply was light. There was no source. No bulbs flickered on. It was as if the very fabric of the cockpit had awakened, emitting a soft, greenish-white luminescence from within. The instruments floated in space, perfectly legible, their faces crisp and clear. The pilots could read every dial without the slightest strain. They looked at each other, their faces bathed in the cool, shadowless glow. There were no harsh reflections on the canopy. It was utterly silent, save for the hum of the inverter. It was magical. One of the crew, a young wireless operator, later wrote in his diary, "It was like sitting inside a giant, friendly firefly." The plane lit itself. There was no on or off. It just was. The official report would call it integrated electroluminescent paneling. But among the aircrews who would eventually use it, the technology earned a more evocative, and utterly accurate, name. They called it the ghost glow. It was the light that had no source, the illumination that lived in the walls, the silent, cool companion that lit their way through the flak-filled darkness without ever giving them away. The accidental discovery in a Dorset hangar had just given them a silent, invisible advantage. The summons from the Air Ministry had been unequivocal, a full demonstration for the Bomber Command top brass. The pressure in the Dorset hangar was now of a different, more potent variety than the simple fear of failure. This was about convincing the men who held the purse strings and the power to deploy technology across the entire RAF. The fate of the ghost glow rested on this single night. The officials arrived just after dusk, a convoy of black Humber cars disgorging a collection of stern-faced men in crisp uniforms adorned with braid and metal ribbons. They were the architects of the night bombing campaign, men who dealt in thousands of tons of bombs and percentages of loss rates. They were pragmatic, hardened, and notoriously difficult to impress. Among them was Air Vice Marshal Sir Robert Sonby, Deputy Commander of Bomber Command, a man known for his sharp intellect and deeper skepticism. The scientists had prepared meticulously. The Wellington bomber stood in the center of the hangar, its silhouette familiar and imposing. But tonight, it was a stage for a revolution. The team, led by Dr. Thorne, stood by nervously. Alistair Finch was at the power console, his palms damp. Sir Robert wasted no time on pleasantries. Dr. Thorne, he began, his voice a low rumble. Your reports have been imaginative. We are here to see if your self-lighting cockpit is a war-winning tool or a waste of valuable resources. Please, proceed. The hangar lights were extinguished, plunging the space into a deep gloom, broken only by the faint light from a single emergency exit. The officers stood in a small group, their faces becoming pale, indistinct ovals in the dark. Dr. Thorne gave a quiet nod to Finch. Inside the Wellington, a flight sergeant from the test unit, briefed earlier, sat in the pilot's seat. On a signal, he flipped the unmarked switch. The effect was instantaneous and utterly alien. The bomber's cockpit, once a black cavity, now glowed with an eerie, uniform blue-green light. It wasn't a light that shone out, it was a light that simply existed within the space. The canopy framed the scene like a picture, revealing the pilot sitting in a luminescent bubble. The light was cool, shadowless, and profoundly strange. It had the quality of deep-sea bioluminescence, a light that seemed alive and organic. It looked less like a piece of 1940s engineering and more like something dragged out of a science fiction pulp magazine. A murmur rippled through the officers. One group captain, a man with a bristling white mustache, took a step forward, his brow furrowed. What is this, a magic lantern show? He barked, his voice tight with suspicion. Are there bulbs hidden in the roof? This is some kind of trickery. Another, a younger wing commander with a navigator's observant eyes, whispered to his colleague, his voice barely audible, this shouldn't be possible. Light doesn't behave this way. It's unnatural. Dr. Thorne remained calm. She gestured to Finch. This was the crucial part of the demonstration, the moment designed to shatter their skepticism. Finch, from his console, gave a signal to the pilot inside. The pilot reached up and flicked the switch off. Darkness. Absolute and complete. The glowing cockpit vanished, swallowed by the hangar's gloom. The officers were left blinking, the afterimage of the ghostly light seared onto their retinas. Before anyone could speak, Finch gave another signal. The pilot flipped the switch again. Light. The same soft, cold, perfect light returned, as if it had never left. There was no warm-up time, no flicker, no sound. It was instant, silent, and absolute. The pilot inside raised his hands, showing them empty, then pointed to the glowing panel behind the instruments, then to the glowing side consoles, demonstrating that there was no hidden source, no sleight of hand. The light was emanating from the very skin of the cockpit itself. The lead engineer, a quiet man named Mr. Abernathy who had overseen the physical installation, allowed himself a small, tight smile. He had seen this reaction before, on a smaller scale. The transition from disbelief to awe was a physical thing in the room. The silence that followed was more eloquent than any cheer. The officers stared, their professional skepticism melting away under the weight of the evidence. Sir Robert Sonby stepped forward, his eyes fixed on the glowing cockpit. He didn't look at Dr. Thorne. He kept his gaze locked on the miracle before him. How quickly can you produce them? He asked, his voice low and direct. The conversation that followed was swift and decisive. The questions were no longer about if, but how many, and how soon. They discussed production facilities, power requirements, installation protocols. The officers approved immediate, priority production. A new, covert factory was to be established, its workers sworn to secrecy. The ghost glow was no longer an experiment, it was a strategic asset. But as the officials departed, their cars disappearing into the blackout, a final, lingering thought remained with the scientists. The officers had approved the what, but they could not, fully understand the how. They saw a brilliantly useful tool, a solution to a critical military problem. But the profound, fundamental physics behind it, the dance of electrons in the phosphor layer, the nature of this cool, solid-state light, remained a mystery even to its creators. They had harnessed a ghost, but they didn't fully comprehend the seance. They were deploying witchcraft, and they were just grateful it was on their side. By the spring of 1945, the ghost glow had become a quiet, open secret among the aircrews of Bomber Command. Hundreds of Lancaster, Halifax, and Mosquito aircraft now flew with the distinctive blue-green panels illuminating their cockpits. It was never a technology that made headlines, its success was measured in silence and survival. Bomber crews, a superstitious and pragmatic lot, developed a profound trust in the gentle light. It wasn't just a convenience, it was a psychological bomb. In the tense, cold hours over Germany, the absence of harsh bulbs and glaring reflections created a calmer, more focused environment. Pilots reported less eye strain and a profound reduction in fatigue on long missions. Navigators found they could plot complex courses more quickly and accurately. The crews felt it gave them an edge, a small but critical advantage in the deadly game of cat and mouse. They swore, in the mess halls after missions, that the ghost glow had saved lives, and they were almost certainly right. With the end of the war in Europe, the frantic production of the electroluminescent panels ceased almost overnight. The secret factory was shuttered, and the technology, like so many other wartime innovations, was declassified and quietly leaked into the stream of civilian research. The scientists of the TRE returned to universities and private industry, their knowledge of phosphors and thin film conduction now a marketable skill. The 1950s and 60s became a period of quiet experimentation. Companies like Westinghouse and General Electric in the US, and Thorn Electrical in the UK, saw potential in this cold light. They experimented with consumer products, creating novel, if sometimes commercially unsuccessful, applications. There were attempts at electroluminescent nightlights, their soft glow a familiar sight in some post-war homes. They were used in instrument panels for high-end automobiles and aircraft, a direct lineage from the Wellington bomber. There were even experiments with rudimentary alphanumeric displays and, whimsically, in toys that glowed with an otherworldly light. For a time, it seemed the ghost glow might remain a niche technology, a curious footnote in the history of lighting. But the principle was too powerful to fade away. The seeds planted in that Dorset hangar lay dormant, waiting for the next technological revolution. That revolution was the rise of solid-state electronics and advanced materials science. Decades later, long after Dr. Thorne had retired and Alistair Finch had passed away, long after the original Trey lab had been demolished, the accidental invention resurfaced in a dozen unexpected places. The fundamental discovery, that you could make a thin, solid film emit light efficiently with an electric field, became the backbone of an entire industry. The soft, even glow of a car's dashboard screen at night is a direct descendant of the ghost glow. The gentle, shadow-free, night mode, lighting in modern aircraft cockpits, designed to reduce pilot fatigue on long-haul flights, follows the same principle. The highly efficient, always visible emergency exit signs in theaters and airplanes use electroluminescent technology for its reliability and low power draw. Most significantly, the research into organic compounds that could emit light, pioneered in the post-war years, led directly to the development of OLED, organic light-emitting diode technology. The flat panel displays on smartphones, televisions, and computers, with their perfect blacks and vibrant colors, are the great-grandchildren of the wartime mistake. Early experimental thin film displays in calculators and digital watches in the 1970s were a direct application of the same science. A desperate attempt to blind enemy pilots, born in the pressure cooker of total war, had failed. But its glorious, accidental byproduct, a cool, silent, shadowless light, had succeeded beyond anyone's wildest dreams. It had saved lives in the air, and then, quietly, patiently, it had gone on to illuminate the modern world. The faulty WW2 light tube, conceived as a weapon, had ultimately given us a better way to see in the dark, a final, peaceful victory pulled from the jaws of a wartime failure. The ghost glow had escaped its cockpit and found its way into the fabric of daily life. Today, the story of the ghost glow is a whisper, a faded footnote in the vast, thunderous epic of the Second World War. It rests not in public monuments or celebrated annals, but in the quiet dust of archives. The documents, Project Icarus, the Transient Illuminator, the Integrated Electroluminescent Panel reports, were declassified not with a bang, but with a bureaucratic sigh. Decades after the war, their dramatic secrets reduced to dry technical curiosities for historians and PhD students to occasionally stumble upon. The men who breathed life into the impossible are gone now. Dr. Evelyn Thorne returned to academia, her wartime work shrouded in secrecy, never receiving public acclaim for the revolution she helped midwife. Alistair Finch, the engineer who first saw the glow on his clipboard, went on to a successful but conventional career in the burgeoning television industry, never fully grasping that the principle behind the screens he helped refine was one he had encountered on that fateful, exhausted night. The fitters, the chemists, the officers who championed it, they passed away, one by one, their obituaries speaking of their service, but never of the ghost they had summoned in a Dorset hangar. They died before they ever realized the true scale of what they had unlocked, the global industry they had inadvertently midwifed. But the truth, stripped of classification stamps and faded ink, is beautifully, profoundly simple. The original mission was a failure. The emission stabilizer, the device designed to fire a burst of daylight at a German night fighter, never worked as intended. It never saved a single bomber by blinding its pursuer. It never stopped a single Junkers Ju-88. It did not, in any measurable way, change the immediate course of the air war. It was a dead end, a dud, a weapon that refused to be a weapon. Yet, in its glorious failure, it changed everything. It changed the very nature of how we create and interact with light. It shifted the paradigm from heating a filament until it glows, to coaxing a solid material to sing with photons. It moved us from the age of the bulb to the age of the panel. And all of it, the OLED screens in our pockets, the dashboard displays in our cars, the gentle night lighting in our aircraft, can be traced back to a single, unplanned moment. It happened because one broken shoebox full of overheated wires, volatile capacitors, and a fragile glass tube behaved in a way no one had predicted, no one had designed, and no one, at first, could even comprehend. The story of the ghost glow is a quiet testament to a humbling reality of progress. Sometimes, the future isn't engineered. It isn't the product of a 5-year plan or a clearly defined objective. It isn't built on a drafting table. Sometimes, it's simply discovered. It is found in the margin of error, in the side effect, in the beautiful, chaotic accident that occurs when human ingenuity meets the stubborn, unpredictable complexity of the physical world. It was discovered in the cold, damp air of a blacked-out British hangar, by tired, desperate people, during a war that no one wanted, but from which a sliver of light, a cool, silent, revolutionary light, somehow, miraculously, emerged.